Yes, okay. So it's a great pleasure to welcome Alina Vdovina to give today's seminar. Alina is, she tells me, originally Ukrainian, who spent time in Moscow, various places in France and Bonn. And she is now at the University of Newcastle. And she's going to tell us about... I forgot to write down your title, Alina.
It's okay.
Yeah.
If I share the screen.
Yes, when you share the screen, we will get it. Or you can tell me what your title was?
It says host disable attendee screen sharing.
Oh, share screen. Allow share. They keep changing things. I don't...
Tenjo, the quickest way is to make Alina a co-host.
Okay, I see. How do I make her co-host?
Well, click on the participants at the bottom.
Yes.
And then go to Alina's name.
Or go to Alina's name, more, okay.
And then the more.
And make
co-host.
Make host, okay. No.
Co-host, yeah.
Yeah. More. In the last week, it wasn't even... okay. Yes. So you are...
In the worst case, I can send you email with my slides.
No, that's okay. So you should be able to do it now.
Yeah.
They keep changing these things. Okay. So building quaternions and Drinfeld-Manet solutions of Yang-Baxter equations. Very good. Well, thank you for agreeing to give this seminar, Alina. And you can begin whenever you're ready. Thank you.
Yeah, thank you very much for the invitation. It's very exciting to talk to theoretical physicists and mathematicians, like to a very broad audience. So don't hesitate to interrupt me anytime, because it's mostly like invitation for discussion. Yeah, so this is the plan. I want to kind of discuss connections between mathematics and physics, but then I'm going to give a crash course on geometric interpretation of buildings, and then hopefully explain how I think about Drinfeld-Manet solutions of Yang-Baxter equations and how they are related to the cube complexes. And I think generally to be useful in a theoretical physics, mathematical structure has to be sufficiently rich and cover several fields of mathematics, physics, and potentially computer science. So it's like maybe Poincaré's upper half plane, and yeah, so there are a lot of examples. But one of the barriers is that there are different languages and different terminologies. So what is my philosophy, that you have to find some kind of example which is interesting enough, but which has features appearing in several fields, and then hopefully you can get some results. So actually, the geometric core, which I'm about to introduce, appears in several fields in mathematics and also has several connections into theoretical physics as well. But I'm going to concentrate on one, but just be aware that we can discuss maybe later after, like at the end of my talk, I'm going to put more like topics and also papers which may be potentially interesting to the audience of theoretical physicists. But as I said, that I'm going to discuss Yang-Baxter equation, and it's a very wide topic and it appears in many places. But what I'm going to do, I'm trying to go back to basics and to like really early 90s, maybe late 90s, and look at it like from a very, very abstract point of view. So I was looking at some papers of Drinfeld, and then I was last year I discussed with Yuri Manin a bit, and it's somehow not just kind of one solution of the equation, but it's I'm going to address like large family of solutions, almost a philosophy. And so after that, there were many follow-ups. So there are like even several communities, but mainly algebraics. People were looking at like a theory of braces, multi-permutational solutions. Actually, it's a whole world, but as I mentioned, I want to go like to the very, very kind of to the core of the subject. And also one of the very few geometric applications, it's to use them as not invariants, but I'm interested very much about nodes. So if you want to discuss this, I would be very happy to discuss it later by emails or by like private conversations. But today I really made my choice like for this connection with Quaternions, buildings, and cube complexes. So we suggest an approach using buildings. So the solutions which I'm going to introduce at the end of my talk, they have like feature of, they have kind of new geometric features, but they also satisfy many known properties of Yang-Baxter solutions. I was checking like many papers and computing some like invariants which I introduced, and actually the solutions which do come from buildings and cube complexes indeed turn out to be new. So the plan of the talk, that first I give the definition of Drinfeld-Manin solutions of Yang-Baxter equations, but then I will introduce buildings and arithmetic cube complexes, and then show how those topics are connected. And of course, like it will take some time to introduce buildings and arithmetic. So if you haven't seen buildings before, in any case, I'm going to give like elementary examples, but in the same time, I will keep the slides with formal definitions as well, because as I mentioned, we have a mixed audience and some people already heard me speaking about those topics. Okay, so first of all, I just say how I think about like a Drinfeld-Manin solution of Yang-Baxter equation. So it's very general. So we talk about non-empty set. Also, sometimes it's called in the literature set theoretic solution of Yang-Baxter equation. But how I define it now, it's even more general than set theoretic solution. So that's why, as I said that I went back to the basics. And I think it's a good idea to give this very, very general definition, because then we can just use it to generate many various kinds of solutions. So think let X be a non-empty set, which goes from a Cartesian product of X with itself to itself. And so R of XY is UV, but more that our solutions have to satisfy this like Yang-Baxter equation that R12, R23, R12 equals to R23, R21, and R23, right? So I will describe like new series of solutions and introduce some geometric invariants to ensure that our solutions are really new. But what I would like to emphasize that here we, like X is a set, but then we can use this this correspondence R in various ways. For example, we can use this as elements elements of the set X. We can use as indexing for like basis of vector spaces and so on. Okay, so I'm about to go to buildings. So are there any like quick questions about the definition? Yeah.
I don't see questions, so I think you can continue.
Yeah. Okay, very
Actually,
good. So,
Charles posted the question in the chat.
He says, what is the product between... Oh, yeah, Charles asks, what is the product between the R's? You mean, Charles?
So just a composition of, it's a composition. So you have a like triple, right? You have a element from R to the power 3, and then you act on the first. So Ij means acting on i's, and j's component of R3. So we have like triple, then we act on R1, 2, right? So we act on the first and second component, then R2, 3 acts on the result, and so on. Okay. So of course I will show an example later how it works, because actually our set X will come from certain labelings in the cube complexes, and this will be like illustrated by geometry of certain cube complexes. Okay, so now let's start discussing buildings. And before the formal definition of a building, I will talk about just one-dimensional buildings, which are just Cayley graphs of saying free groups. And I will remind the kind of standard topology that if we have a like saying four-valent graph, and then the fundamental group of this just wedge of circles, it's a free group in 2 generators, and the universal cover, it's an infinite tree. So I will refer to this picture several times, because actually it's a very, very nice picture, because you have action of the free group on the infinite tree of valency 4, and then the quotient by the action of the free group, it's a wedge of 2 circles. And of course, when you talk about like graphs and infinite trees, you don't need to concentrate on this kind of labelings and thinking about the combinatorics and arrows, because the combinatorics here, it's quite obvious. But when we go to the higher dimensions, because I'm going to talk about higher dimensional objects, maybe dimension 2, but then dimensions 3 and higher, then it's really important how do you kind of identify your edges respecting orientations, and how do you organize your squares or cubes or like other objects. So, and so what, when we go to higher dimensions, we will have like chambers and apartments, and this is an example of an apartment of a higher dimensional building, which is going to be some kind of tessellation. So in a way, we have, so how the motivation for buildings, and also how I look at the buildings, is somehow generalization of a branching structure like a tree, but then instead of each infinite path of a tree, we have a tessellated plane. But yeah, so, and then all for three-dimensional buildings, we have tessellated three spaces and so on. So just to give a flavor, what is the building, right? It's like many tessellated planes or spaces, and they intersect with each other, and so on. So now we are ready to give a formal definition of a building. So think n-dimensional hyperbolic or Euclidean building. It's an n-dimensional complex, which is a union of tessellated spaces called apartments. And then for any two chambers, there is an apartment containing both of them. And if two apartments have non-trivial intersection, then there is an isomorphism fixing their intersection point-wise. So for one-dimensional building, you can immediately check that the example of an infinite tree, which I gave a couple of minutes ago, indeed fits that the apartments are infinite paths in a tree, and chambers are just edges of the tree. And then it's clear that if you take two infinite paths in a tree, then they are all the same. And also, if you take any two edges, which are chambers, you can always find an infinite path which contains both of them. So, but then to define more interesting buildings in dimensions 2 and higher, we need more terminology, but actually all this kind of additional combinatorics which we define will be used later, like for this solutions of Yang-Baxter equations. So when I say like a polyhedron, it's a two-dimensional complex which is obtained from decorrected polygons by identification sides with the same letters respecting orientation. So of course, if you would just have one square with the word A, B, A inverse, B inverse, then it would be like usual picture of a torus. But now we are already in a more interesting world, like really we want buildings. So we need more like polygons. So here, like an example of a polyhedron, it's like four squares. And then we identify letters with the same labels respecting orientations. Okay, so this is the kind of smallest non-trivial example. And then another definition we need, it's a so-called link, but it's not a link from knot theory, it's like link from geometry. And how we can think about it, we take a sphere of a very small radius at the point of a polyhedron, and then the intersection of the sphere with the polyhedron is a graph which is called the link at this point. So here it's somehow elementary polyhedra where we just have one, so we didn't make all the identification, we just take one edge and glue four squares. But then what is the link? So there are two vertices, and the links at those vertices are just one black vertex with four edges. So this is somehow, this notion of a link, I think it's not very much used yet in the kind of theoretical physics. What is my impression that people mainly work like with like saying Riemann surfaces, manifolds, that the kind of these branching structures are not yet widely used, but I think that this can be kind of useful. So anyway, this is the definition of a link. So any questions?
I don't no, we're okay so far.
Okay, good, because like I give some maybe some non-familiar definitions, so I want to be sure that everybody is on board. Okay, and then we will consider also thick polyhedra, which means that each edge is contained in at least 3 polygons. So here, like the edge A1 is contained in 4 polygons, and it means that if we have like larger objects, so for example, if here we will identify all the rest, so we identify A2 with A2 and all A1s are identified with itself, then our polyhedron will not be embeddable in a 3-dimensional space anymore. So we need some kind of methods. How do we work with such objects? So this is an example of a link. So if in the previous picture we identify all edges with the same label respecting orientation, then it's like kind of homework exercise. We will get a complex just with one vertex. And if we look at the link at this vertex, it's going to be this graph. It's going to be complete bipartite graph 4, 4. And each vertex of this graph will come from an edge of the polyhedron. So now if, for example, we come back to this picture, we can look at them, for example, edge A1, right? So we see that there are 2 vertices coming from A1, like from A1 and A1 inverse, and both of them have valency 4. So it's like here, right? So we have like A1, A1 inverse, and both of them have valency 4. So now you can understand why I didn't draw the whole polyhedron, because first it's not embeddable in a three-dimensional space, but then we would have this link as like the link of a polyhedron, so it would be really messy. So I just showed how vertices A1 and A1 inverse look like in this polyhedra.
Sorry, Alina, these remind me of Hasse diagrams.
It's an interesting question. I don't know. No, we have to discuss maybe later. So this was my goal, that people just maybe you write somewhere your ideas to what it can be related to, right? So I don't know this connection, but it may be some new connection. Yeah, so there are a lot of such kind of graphs of diameter, saying here it's diameter 2, so the diameter is the maximal distance between 2 vertices, and the girth is the length of the shortest cycle, it's 4. So it's like diameter m and girth 2m. It's so-called generalized polygons, and it's kind of a classical result of Fate and Higman that this m can be only 2, 3, 4, 6, or 8. So I've just chosen this kind of the easiest way to talk about m equal to 2, but of course, like there are other interesting cases as well. Yeah, so this is about the links. And you know, now, even if you didn't didn't think about buildings before, now you can already imagine them, because in like mid-90s, there was a very nice paper of Ballman and Brin that if we have a compact 2-dimensional thick polyhedron, then if all links are graphs like of diameter m and girth to m, then the universal cover is a 2-dimensional building. But actually this theorem can be also translated in like higher dimensions. I don't know if anybody written it kind of formally. Today I will talk only about very, very special kind of higher dimensional buildings. So we don't really need something, a theorem like this, but it's kind of a good good illustration how to think about higher dimensional buildings. But of course, like again, if we come back to my example from the first slide, when I had just the vertex, one vertex graph with two loops, and then the universal cover is a building which is just a tree, right? It's kind of elementary, but when you go to higher dimensions, it becomes like more involved. But in any case, the idea is the same, that you look at some finite object, but then because like analyzing the properties of this finite object, you are able to control the infinite dimensional object, and also you are able to kind of control the boundary of this infinite dimensional object. Okay, but then like the natural question is how to construct such a polyhedron, and then it turns out that it's like combinatorially difficult, so you have to come up with some new ideas. And it was like during my time in Bonn, around 2000, when I came up with some kind of very general combinatorially / geometric notion. So you don't, I just put it on the slide to have kind of completeness of the talk, but you don't need to think about it, how it's how you can interpret it. It's just to get polyhedra with given lengths and with the properties we want. We want to somehow encode this labelings of the sides. So it's not just any labeling, because of course, if you want to construct a polyhedron with certain properties, and if, for example, you try computer search, it would be a nightmare. So you need some rules, how you label the edges of your polygons. Then you identify letters with the same kind of the same labels, with edges with the same labels, and then you get a polyhedron which you want. But the reason I somehow still am putting this definition, because in this kind of, when I saw this kind of definitions of the set theoretical Yang-Baxter, of the solutions of Yang-Baxter equations, I saw that we somehow have kind of bijection between pairs of elements of a certain set. So indeed, this also, the connection is not so straightforward. It's not that from every polygonal presentation you can get set theoretical solution, interesting set theoretical solutions, but it's very, very much connected. And I will give some examples. So this is what I already mentioned, that it's somehow this way to have polygonal presentations. It's a kind of explicit way to get graphs with given lengths. So in the theory of buildings, and like in geometric group theory, very often people say, okay, there are like existence results. So maybe like from the general theory of Jacques Tietz, who kind of introduced buildings, one could deduce that, okay, we can get, saying, polygons with polyhedra with certain lengths, but it's clearly not explicit, because yeah, very often like the theory of buildings is the theory of algebraic groups, which is very kind of non-explicit. Okay, so actually now we already introduced buildings, so the crash course on buildings is already over, and now we are going to go to number theory. So what is my idea is to introduce some geometry, combine geometry and arithmetic. So in this sense, like if you talk about trees, then you know there is a very good book of Jean-Pierre Serre, Trees, where there is a lot of arithmetic introduced on trees as well. But if you go to like the higher dimensions, your life becomes even more complicated. So saying as a reference in case of trees, then of course this kind of Bas-Serre theory in the book of Serre on trees, it's a very good reference. But what I would like to do, I would like to now introduce how we could proceed and go, how do we go in higher dimensions. But we come back to like Jacobi, and so like very elementary example. Actually, this example is from Wikipedia. So like if you just take a number and want to present it as a sum of 4 squares. So saying if 1, how do we represent 1 as a sum of 4 squares, right? But of course, we can formulate Jacobi's 4-square theorem in the way I would like it to introduce. So the number of ways to represent n as a sum of 4 squares is 8 times the sum of the divisors of n if n is odd. And then also if p is an odd prime, then the number of solutions is 8 multiplied by p plus 1. Okay, so it's like very elementary number theory. But then, so saying let's have more restrictions. Let's have prime, which is 1 modulo 4, but actually this restriction is not essential. In general, we can look at any primes, but then this kind of the mathematics becomes less obvious and a little bit more messy. So it just kind of to illustrate it, it's enough to have it modulo 4. But then so if we restrict our solutions in such a way that one of ij is odd, and we, without losing of generality, we say that a naught is odd, then the number of the solutions is p plus 1. But then now we can talk about quaternions. Okay, here we talk about integer quaternions. So of course, like in Dublin, everybody knows the definition, I'm sure. And we present them in this way that if we say that the quaternion norm is equal to p, then this set SP of the integer quaternions has size p plus 1. So saying this interpretation for quaternions is just a reformulation of the Jacobi 4-square theorem, right? But then it really has quite nice connections, how you can put arithmetic on trees. So like if we look again at we take prime, which is 1 mod 3. Then if we look at the equation x squared is minus 1 mod 3, and it has solutions in z, but then it also, this by so-called Hansen's lemma, this solution can be lifted to the p-adic numbers. And why it's interesting, because it gives us a way to interpret our quaternions by 2x2 matrices, right? We can take this solution, IP, and put it into the matrices. So I'm sure that probably you are aware of this representation, but it has some kind of nice application And so how it's related to our talk today, that in fact the set, which is xi p of sp, contains p+1 elements and generates a free group with p+1 divided by 2 generators inside of PGL2 QP. And this group, the free group, acts freely and transitively on the vertices of the regular tree of valency p+1. Of course, since p is odd prime, so that p+1 divided by 2 is an integer number. And so the application was of Margulis and Lubotsky-Philipp-Sarnak for so-called Ramanujan graphs. So it's saying Ramanujan graphs and Ramanujan complexes. It's another topic which I like very much. It's somehow graphs and complexes with interesting spectral properties. But again, you are welcome to ask me like by email or later, because I don't concentrate on it today, but it's indeed quite an interesting topic. But my point here that we can, so if we are clever enough that we can introduce extra structure related to the, so in this case to the infinite tree, but in our case to buildings and complexes. But of course, if we go to like complexes of higher dimensions, then it's not that elementary anymore. So I will, of course, about the higher dimensional arithmetic, I will not give like very precise constructions, but I will give some examples. Yes, so indeed, like, can one get similar results to Margulis and Lubotsky-Philipp-Sarnak for products of trees? So there were some examples in early 2000s of Burger, Merzes, and Ratagi, but it was like there were some restrictions that your trees had to be of different valency. But then it turned out that the most interesting case for complexes is to have trees of the same valency. And also when I talk products of trees, I mean Cartesian products, because also I realized that several times I was given talks in communities like more related to theoretical physics or category theory. Then very often when you say product, people think more about tensor product, but here we talk really of Cartesian products of trees. Yeah, so like and saying to have the same valency in the trees is interesting, because then we can get so-called Ramanujan complexes. But again, it's not enough to have the same valency of trees. You also need to have like some additional arithmetic construction. So what is difficult, like for products of trees of the same valency, that it turns out that from classical Hamiltonian quaternions, you have to move to more general quaternionic algebras, and the quaternionic multiplication becomes the following. So you have to introduce one more like transcendental parameters, but it's like to go to dimension 2, it's enough to have one parameter, but then like we have examples with many parameters. And I think this kind of those additional parameters can be useful for constructing more and more solutions of Yang-Baxter equations. Okay, and then so how it's related to our groups. So actually I started my talk with an example of 4 squares, and then how we get polyhedron with 4 squares, but actually it was not just arbitrary squares. Actually, those squares were coming from this kind of quaternionic algebra. And so as I already mentioned, what is difficult when you when you need to get polyhedra with certain properties, you have to be sure that your edges are glued in a very specific way to get very specific links. And it turns out that quaternions are very useful. So it's of course like the proofs that everything works in the way you want. It's a non-trivial kind of number theory, and I have a series of papers with Jakob Stix, who is a number theorist, in this way. And you have to kind of go from geometry to number theory and from number theories back. But then you are kind of lucky that you, for example, in this example, you can plug in, instead of A1, A2, and so on, you can plug in these quaternions, and you will see that they kind of cancel out. Yeah, so, but then how, again, it fits to the picture which I had before, that we have this, again, like every example which I give, it's it belongs to an infinite family of examples. So how this building where this group acts look like, it's like all the apartments are planes tessellated by squares, and all the links at all the vertices are complete bipartite graphs, also like the graph which I showed them in the beginning of my talk. But then, in addition, this group, which is a fundamental group of our polyhedron, turns out to be an arithmetic lattice. And here, like again, the word lattice is overused everywhere. So here it just means a discrete group with certain properties. And this group has like very nice representation, which can be also potentially useful in many places. So you see, indeed, you can find explicit matrices. How do you embed your group into the direct products of linear groups? But yeah, so, but it's why I say that it's arithmetic lattice. So even so, it's embedded into a direct product of 2 copies of PGL, but it's irreducible lattice. It cannot be presented as a product of 2 groups. So that's why it's kind of interesting from the number theoretical point of view and point of view of geometric group theory. Okay, but then I just summarized our results because the precise formulation is a bit technical, but what I would like to say that with Stix we can explicitly construct quaternionic groups acting simply transitively on products of trees of any valency, and then to have like families of groups which are not just not isomorphic, but they are even not commensurable. So it's like, as I said, that it's usually hard question to compute, to have examples of groups which are like in the same time arithmetic lattices as well. But now, another example already for, let's go to the dimension 3. So quaternions can be used also to get cube complexes of any dimension for any set of primes. So if you take any set of odd primes, so like saying K or odd primes, you can get a cube complex of dimension K. But again, I will give just the easiest example, 3, 5, 7, right? The smallest set of odd primes. And again, of course, there is a like theory behind it, but how it looks practically, that we can find such quaternions and then also like label them like A1, A2, and 3, so on, in such a way that those labels can be put into cubes. And for example, like we have this group gamma 3,357 quaternion group, and now if we put those words on sides of squares, and then we can put those squares in cubes, we get cube complexes covered by, so in this case covered by a Cartesian product of 3 trees. But then finally we can go back to Yang-Baxter. So the geometric realization of this group, which I was talking about, consists of 24 cubes, and this is just one of those 24 cubes. But then let's go back to our definition of Yang-Baxter equation, when we have to find this bijection R between pairs of elements. So the set X, it's the set of labels of the edges of the cubes, but each edge appears together with its inverse as well. So if you have like A1, but then we have A1 inverse as well. So here we have like 18 different, so this set X has 18 elements. So, but then the most interesting, how do we form this bijection of pairs? So we pick every square, and then if we have a square with a label xi, xj, xk, sl, then R of xi, xj equals to xl inverse s xk inverse. So in this 357 example, we get this matrix 153 by 153. Okay, so any questions? Because this is the way how do we get the solutions of Yang-Baxter equations. We get them from the sides of the cubes.
I don't see questions at the moment, but perhaps.
Yeah, very good. So then we can continue. So I know I can illustrate how to verify that Yang-Baxter equation is satisfied. Of course, it's like theoretical. There is a theory why indeed it's satisfied, but just to illustrate it in this cube. But again, it's just one cube, and there are 24 cubes glued together in such a way that it's very difficult to kind of to draw it. But still, like just only one cube. What we do, right? So we take A1, B1, C2, and then when we take like R1, 2 from A1, B1, C2, so we act on the first two components. So we have A1, B1, and it corresponds to the square, to the front square. So the label of the front square is A1, B1, A2 inverse, B2. So that's why it's B inverse. So A1, B1 equals B2 inverse A2. So we change A1, B1 to B2 inverse A2, but C2 we didn't touch. Then now we have to use, we have to act by R2, 3. So the second and third component, it's C3 inverse, A1 inverse. So we look at them. So this is the right-hand square, which has a label A3 inverse, A1 inverse, C2 inverse, A2 inverse. So that's why A3 inverse, A1 inverse equals A2, C2. So we proceed. So we get that, we get C4, B2 inverse, A1 inverse. But then if we use R2, 3, R1, 2, R2, 3 again, right, to A1, B2, C2, we do exactly in the same way, and we get exactly the same vector. But now I can mention what is the new invariant. I meant in the beginning of my talk that how do we distinguish different solutions, and also like from the existing one, that actually this group gamma is an invariant of the Yang-Baxter solution, and it's different from the so-called structure group defined in the algebraic community. And we can, so why for example here we can show that this solution which comes from this cube complex, why it's completely new solution, because gamma is arithmetic lattice, and if we use this kind of structure group from early work of Ettinghoff and his collaborators, we get that in their structure groups are kind of solvable groups, and yeah, so actually it's like a bit technical, but I mean that we use the way that our group is arithmetic, and it doesn't have any infinite quotients, and all the examples which I've seen in the literature, they do have infinite quotients.
Sorry, can you show us the definition of gamma again? Just
yeah. So this is just one example. It's one of the many, and yeah. So it's it has 18 generators just for the simplicity. Like here it's written I plus 12, right? Not to make it messy with the inverses. Yeah. So it's so what is the structure, right? So if you actually it's indeed quite counterintuitive when you go to complexes of saying dimension 3 and higher, because in a way that is, so here like the 3-dimensional example, it's a blend of 3 2-dimensional and not like 1-dimensional, because saying the example which I showed, the 2-dimensional example which I showed in the beginning of my talk, right? It's like 4 squares, there is alphabet A and alphabet B. So it's like horizontal and vertical. But then when we have like one more direction C, what do we have here? That if we fix like 2 directions, A and B, we have a 2-dimensional example. So B and C, it's also like polyhedron, which is covered by product of 2 trees. And if we fix B and C, it's also covered by product of 2 trees. But then really by miracle, it's indeed like kind of non-trivial construction involving Quaternion algebras. In this case, indeed, we kind of, we can put them on the sides of the cubes, and they are compatible. So apparently this kind of compatibility condition appears again in several fields of mathematics. There is like whole world of so-called like K-graphs and sister algebras coming from them. There is this kind of compatibility condition. And apparently this compatibility condition also kind of manifests itself in this kind of Yang-Baxter solutions. Yeah, but then as I said, that this is kind of for Dublin very nice connection that apparently to ensure this kind of compatibility conditions, you can use quaternions. As I said, of course, to justify that you can indeed find such sets of quaternions that everything kind of cancels if you multiply it together. But nevertheless, yeah, so it's a indeed like set of quaternions which can come together in like kind of higher dimensional complexes. But what is even more striking that indeed you can use it to any dimension K, and it's like families of examples and families of cube complexes of any dimension. And what I also think that I just started with this Yang-Baxter equation, but apparently I saw that people in physics are interested also in this kind of n-simplex equations, where it's not just 3 components, but with like 4 components, like what they say tetrahedral equations. There are different terminology, and I think these kind of higher dimensional complexes can be used to get solutions of those equations as well. So this is kind of just the first try. Yeah, so thank you very much for your attention. And just maybe I put some more topics, what we can do with it, but every topic I put, it's I already have some results in those directions, but it's just where you can look at it. Yeah, thank you very much for your attention.
Okay, thank you very much, Alina. Questions? Let's see, there's one chat question here, which, let me see what. Yes, Bal has questions. Where? I think you can unmute yourself, Bal. Just it may be faster than me finding you.
Okay. The question is, from what I know, the Yang-Baxter equation comes in physics in terms of the braid group as the commutant of the co-product of some quantum group or something like that. Okay? And also it leads to Hecke algebras and not invariance. What is the situation here? And do you get this extended Yang-Baxter, which has a parameter V, which comes in integrable models?
So, like the last question, actually, so I don't know exactly what you, but first about the braid group, it's quite interesting. It turns out the braid group, because I'm a geometric group series, right? The braid group is really very, very big. So in fact, and this group which I'm talking about, it's like in a way smaller. It's just infinite. It doesn't have any infinite quotients anymore. So apparently, my group can be presented as some kind of quotient of a braid group, and already has also some representation. So very good that you kind of started this topic. So indeed, every time you can get many like representations of the braid group from my construction, but you can get even like more of the extra structure, right? So when people talk, so one of the ways to get from this R metrics, which I suggest, but it's like it's not just I suggest, it's like more classical. It follows from Drinfeld. So his original way was to look at this Yang-Baxter classical Yang-Baxter equation, and V can be any, like it's, for example, can be C, right? It's just any vector space over some like field. But then the solution is when V is spanned by X, right? So actually X gives you like many solutions, but yeah, so it's actually very interesting. So, but then what, I didn't catch your last question.
The question was, do you, first is, this leads to integrable models and also to Hecke algebras in the thing that we know. Okay? And there's also the issue of the Schur-Weil duality. Somehow the break group is the dual of the quantum co-product of the quantum groups. Is there such a thing here also for this?
So
the break group?
So the simple answer is yes, because if so, what we do, right, is so as I mentioned, that we go back to so as I said, that I started with this very, very general definition of like which goes back to Drinfeld and Manin, but then we can introduce. So if I take one of my solutions, then for example there is a like there are follow-up papers of which use like Manin and Drinfeld, like of Ettinghoff and collaborators. So what I try to do, if I take any of my solutions, that all the existing theory does apply to it. So all the existing, so that's why, like, I think this, your question, how Hecke algebras are constructed, this goes back to a paper, I think, of 98 of Ettinghoff with several collaborators. So indeed, you can do everything what is already done. But what is my question? How can we use this extra structure which I get? That, for example, in the three-dimensional case, I used classical quaternions because this kind of more general quaternionic algebras become a bit messy if you go to the dimensions 3 and higher. But still, what I think that, for example, this extra parameter which you get almost for free, that it can be also useful for something, right? So that's why it's kind of invitation to discuss how you can use this extra geometry of like cube complexes and buildings, because yeah, so all the existing theory does apply as well, but there is an extra structure.
I have one small question. You talked about compactness, but what was the topology when you talked about compactness?
When
you mentioned compactness at some point.
Yeah. So then I mentioned, I was just yeah, it's a good question as well, because I was talking about Wallmans and Brin. I was talking about compactness because our complexes, so of course I was concentrating kind of on combinatorics, but in a way that we can put Euclidean metrics, for example, on our squares, right? For the examples which I had on my talk. So we can say that we have a set of unit squares with Euclidean metrics, and then we just really identify letters with the like respecting orientation. So it's like finite compact complex. And but just why I didn't emphasize too much of this kind of geometry in topology, because the combinatorics of the links ensures us that the sum of the angle at each point in the building is exactly 2 pi, and then like we have a Euclidean metric, yeah, but then we can also do the hyperbolic buildings and so on. So very often, like the combinatorics and number theory and like geometry, they all go together. That apparently I didn't mention it because it's of course, I wanted to concentrate on one topic, but one can do even like harmonic analysis on buildings. And I have a series of papers where like my collaborators are like geometrists and working in analysis. They even don't think about combinatorics at all. So this is what I mean, that those objects have like several sides.
Werner, you have a question?
Yes. You briefly mentioned that you also have studied what goes on at infinity, at the boundaries.
Yeah.
And of course, a big thing in theoretical physics is this holography stuff, where things which go on at the boundary are related to things going on in the bulk in a different theory. So could you say a little bit about the boundary issue?
But it's very, very interesting, because it was actually the connection was not very good. So can you tell me what you would like to have about the boundary?
Well, firstly, just what is the language you describe behavior at the boundary, and what are the mathematical structures you get there?
Okay. Yeah, so we can start with even this kind of the very first, like with the very elementary example. It's when we have just, but I'm sure you know this way, but just to check if it's the same language. So here, like saying, if you fix a point in an infinite tree, then you can look at the semi-infinite words. And so if you just have a semi-infinite word, it's just one point at your boundary. But then for a tree, it's totally disconnected circle. But then you can also like, you can look at the continuous functions on the boundary, and what is the kind of natural object here. It's to look at the cross product algebra of functions, of continuous functions on the boundary with the group. But then also they have like unitary representation, and here it's kind of connected to like Kunz algebras and Kunz-Krieger algebras and so on. But for the buildings, it's like more, of course, here the boundary is just a circle, right? But then for the buildings, the boundary becomes like how we define the boundary. The boundary we define as equivalent classes of sectors on a building. And there are many definitions of the boundary. So that's why I said that it would be, maybe we should discuss them how by email or later, because actually there are many definitions in geometric group theory for the boundary. So as I said, that from the point of view of one of the things I'm interested in, the relation with like sister algebra. So there it's like the definition, the best definition of the boundary, it's the definition with sectors. But there are other problems where you can look at different definitions of the boundary. So in sometimes like when you look at the hyperbolic building, sometimes like your boundary is like Menger curve, but sometimes it's kind of, you can for the products of trees, it can be like Cartesian product of circles. But then also I have worked like on higher dimensional analogs of Thomson group, and with certain definitions, it can be like various, it's actually isomorphic to homomorphic to a Cantor set, but with kind of Cantor set with a very, very complicated structure. So it really depends on the problem. And that's why I say that if you describe me what you need, right, then I can kind of cook it up in the way, most likely one can cook it up in the way you need it.
Thank you.
Are there any other questions? Well, if not, let's thank Alina again for...
I have one question. May I ask one question?
Please go ahead, yes.
Okay. You mentioned Kunz algebras.
Yeah.
I they come in a very deep way in algebraic quantum field theory.
Yeah,
And
no, that's why I would be interested to discuss. Yeah.
how does it come here?
Yeah, so here, it's with this graph. So here actually it's not, it would be not quite Kunz algebra on two generators. I think it would be, it's so-called like Kunz-Krieger algebra on four generators, but it's very nice geometric interpretation. So if you look at the, this is what I just mentioned now. So if you look at the boundary of this graph as semi-infinite words, then this Kunz-Krieger algebra is isomorphic to the semi-direct product of the infinite of the continuous functions of the boundary with this free group.
Is it also C-star algebra with isometries as generated?
Yeah. Yeah. So no, I have like the whole theory. Maybe again, like we should just please send me email and I can send you some also slides and papers, because of course it's the whole world. Yeah, I just actually last week I talked about it on Arthur Jeffy's seminar in Harvard, right? But of course you cannot go to all the seminars. It's very interesting because it goes like together with Thompson groups. So it's actually another topic which I'm interested in, to generalize like John's theory of Thompson groups and Kunz algebras and so on, like to higher dimensions. But I would be very interesting to discuss, because indeed all those objects indeed give this kind of nice algebras, but also why I say that it's a kind of nice way to generalize like Kunz algebras, because also all these algebras to associated to buildings and to this polyhedra which I was talking about, they are classified by their K-series. So you can really distinguish them, and also using this geometry. So actually I do have some a list of papers. So you can get you can compute the K-series of such sister algebras very explicitly using the geometry. So you can indeed give explicit K-series groups.
Okay, thank you. Yeah.
But for me, it would be very, very interesting to find like really what are the good connections with theoretical physics, because the languages are always slightly different in how people think. So that's why it's difficult to find exact connections. And that's why I wanted to start with something elementary. So I see that there is this kind of relation with Yang-Baxter equations, which immediately like fits very well to the framework which was already done, but this was kind of more invitation to discuss.
If you can send some references to, say, Denjo, I can pick it up from him. I'll appreciate that. On Kunz.
Sure.
Kunz-Krieger.
Just, can you comment on the K-theory of your very first example, the two squash circles?
So the K-theory of the two squash circles, it's
is it the K-theory of a torus?
It's Z cross Z.
Yeah, it's the K-theory of a torus, which is so that's the squashed. That structure crops up very naturally.
Yeah, of course.
Does the same structure crop up in the higher dimensional example? Yeah. Is there a bigger geometric that you can think of? You're calculating the K-theory of.
Yeah, indeed. So no, it's very good that you immediately said that it's like that you. It's amazing that you calculated it explicitly that it's Z cross Z, because actually the way I also kind of came to this kind of K-theory, because many people look at the same objects and very often they look similar but not quite the same. So actually with the picture of two circles, you can think about Kunz algebra if you think about a semi-group, right? And then or you can think as a free group, that if you're allowed to go both ways. And the K-series is different, so it's like, it was my first exercise how I distinguish them. But then in the higher dimensions, it works exactly the same, right?
Okay.
Kunz algebra has torsion in the K group, no?
Sorry?
The Kunz algebra, there is a torsion, no? Is in
Yeah. It's indeed. And here it's like and how you can recognize it in this particular example, that Kunz algebra is torsion, and it's if you look at this kind of Kunz-Krieger, it's Z cross Z.
Okay.
But in higher dimensions, and so the idea how like to compute K-series in higher dimensions, that those kind of geometric bits and pieces you use them as an alphabet. So for example, here there is so-called like transition matrix, so it's like 4x4 transition matrix. But in how you work, and like how do you work on the graph, right? So if you start with point E, there is a way like you can go to A, you can go to B, from B you can go to A, B, and A inverse, but you cannot go from B inverse. So it's just kind of a combinatorial way how you get transition matrices. But then you can generalize it to higher dimensions.
Okay. Thanks.
Okay. Very good. Thank you. Let's thank Alina again. Yeah. So I'm going to stop recording.